Uh, Welcome to Huna Optical Electronic Technology Company. Today we'll show you many class of optical frequency counts, and this mini class is tell you how to build an optical frequency count from scratch. In this video, we will talk about four main things: where optical frequency counts come from, and which is also can call what is optical frequency count, and how to get an optical frequency count, and how to building an optical frequency count from scratch, and what the finished device looks like. So let's get started and explore the fascinating topic together. First, let's start with a simple question. How do you know what time is it right now? Maybe you can answer, you can check your phone, your watch, no matter it's Apple Watch, or answer, you can get the time from the clock or the calendar. But have you ever thought about how this device actually keep time? What do they use as a timing reference? Before we answer that, let's take a quick look at how people have measured the time through history. Timekeeping is about finding a reference point and counting how often it repeats. By multiplying the numbers of repetitions by the time interval, you can get the total time passed, so you can know which time is it now. In ancient times, people used the sunrise and sunset, or changes in the seasons and the plants to tell the time. But these methods were not very accurate. So to improve this, the ancient Chinese invented the standard dividing the day into equal parts and then into 12 shichen. In this picture, you can see this is 12 shichen, which made timekeeping more precise. Later, they create the water clock, which uses the steady drip of water to measure time even more accurately. Over long time, they noticed the unique features of each season. You can see in the spring, in summer, in autumn, in winter. And so they developed the 24 solar times to help guide farming activities. And with the technology advanced during the first and the second industrial revolution, steams and the mechanical clocks become the main way to keep times. We have arrived at the electronic age. The scientists found that some crystal vibrate at a steady rate when voltage is applied. By counting this vibration, they could measure time more accurately. So crystal oscillator become important. But as technology keep improving, even crystal oscillator will not process enough. Scientists then turn to automate materials and create the system clock, which is now the standard for defining the second. And the such clock we all talk about is it have a name, it's microwave automatic clock. And this is the core of the information age. Today we use this microwave automatic clock to definition the second. Still, this method have their own limits. As the technology more improved, how to get more precise clock. As cold atom physics advanced, especially with laser cooling, scientists wonder if cooling atom could make their resonance even more stable. This will lead to the development of the optic clock, which uses laser to cool the atom and reduce thermal noise, making time measurement more stable. So we built the optical clock And this is the core of the next generation spectrum definition. This is also we call it if you run it more than 30 billion years, we will get 1 second error. But we can build this optical clock. How to measure the frequency so we can get the time clock? On the right, this is the technical we call frequency we call frequency multiplication chain or frequency division chain. So the scientists use these complex systems to measure the optical frequency. You can see they use many optical, they use many lasers and using many physical clothes to transfer the stability. And they put the optical frequency down to the microwave range so it can be measured. This is the image to show you the complete optical frequency division system. This is the picture from the NIST. So we can see they have some disadvantage of such technology. First, they need much more need a large area to put these things. The second, such system is complex and the signal transmission will introduce the error and we can not to eliminate it. The second, if we want to measure much more higher frequency, we will need much more laser and much more physical groups. So such technology have a small measurable range. And to solve this problem, scientists developed the optical frequency clock. Allow me to introduce two great physicists, Professor John Hoare of NIST and Professor Theodor W. Hensch from the Max Planck Institute in Germany, who were awarded the 2005 Nobel Prize in Physics of their contribution to the measurement of light frequency. And as the name suggests, it is a comb used to measure the optical frequency of a laser. So to generate this comb, the frequency of each tube must be fixed, and the frequency interval also can be fixed. So it can work as a ruler for measurement. And if you have studied the digital signal processing, you might notice that this kind of ruler in the frequency domain appears as an ultra narrow pulse signal in the time domain. The repetition of this pulse signal, the repetition, is equal to the frequency interval. So if this be stable, the frequency interval will be stable. And so the repetition rate of the pulse signal is the key part of the optical frequency count. So we get the first things. We need to get a ultra short pulse laser, whose repetition rate depends on the length of its cavity. With an optical frequency count, we can now measure the optical frequency. And with an optical frequency count, we have a ruler that connects optical and the microwave domain. This means we can measure optical frequency count with just one instrument, without needing a complexity several of phase-lock loop system, and we use the optical frequency count to down-convert this laser. You can see this is an optical automatic clocks picture, and we're using a laser. It was very stable, and the laser frequency is log to the atomic resonance in there. And then we use a optical frequency counting. Now convert this optical frequency to the microwave frequency, then we can measure and then we get the time. So this will put the optical clock from a huge air to become a small instrument. Now we know what optical frequencies can do and where they come from. The next question is how to get optical frequency. As we mentioned, the optical frequency comes appear as an neutral short pulse in the time domain. So first, the challenge is how to create this pulse. And the second question is, if we get this pulse, how to get the optical frequency count? We need to lock the two freedom of the neutral short pulse, which we call the rotation frequency, and the carrier envelope offset frequency. After we lock these two frequencies, the output pulse of this laser is stable and we can use it to measure. So it can be called as optical frequency count. So the first question is how to make this neutral short pulse generation. The simplest way is to find a material that keeps narrowing the input pulse over many cycles until it becomes short enough. Such things we call the steerable absorption. So the steerable absorption is essentially selective transmission. Its transmission varies with light intensity. Some diamond molecules can do this under certain conditions, but they are not very stable. So researchers look for sterile materials that could do the same job, leading to what we now call the true steerable absorber. Include the system, the carbon, the graphene. But these things have some advantage. It's very easy to realize the mode locking. It has a compact structure. It has a very high short-term environment stability. But it also have disadvantage. We can imagine if you want to using such laser for more than 1 year, 2 year, or 10 year, the material will get damaged. So the long-term stability is poor, and the relative wide optical pulse-wise, there are often generations of picosecond range, and the optical noise is higher. So to improve this, researchers have to find other ways to realize the steerable absorbing. They call artificial steerable absorber. The two types of this is all the fiber-based structure. One is called nonlinear polarization rotation, which uses polarization loss for space device to narrow the pulse and create neutral short pulse. And this structure has advantage at it has many tunable parameters. You can see the things can all be tunable. So it can customize the structure and the pulse wise. And the output pulse wise is very narrow. It can generate the femtosecond signal range, and it have much lower the optical noise. But it also has a disadvantage because it using the polarization, it has low environmental stability, and also because they are using an optical, is using the uh, using not fully fiber-based structure, so it will be very easy to lose the monologue. Another types of such structure is we call the nonlinear amplifying loop mirror, which we also call it the 8 cavity, the figure 8 cavity and the figure 9 cavity. And it also has the advantage which, because it's a fully fibrous structure, it has higher environmental stability, and the output pulse wise is also very narrow. It can reach the 1 second range, and the optical noise is much lower. But it also has disadvantage. So monomark injection is much higher because it using the reverse phase shifts to narrow the pulse by causing interference between the forward and backward phase shifts. So, how to solve the self-starting challenge in nonlinear amplifier loop mirror based model laser? This is the core challenge of the figure 8 and also for the figure 9 structure. But the scientists find much more ways to solve this problem, so we do not talk about this anymore. And now we get the usual short pulse. Then we need to make it stable. So there have two key features. The pulse repetition frequency, which mainly depends on the length of the fiber cavity, and the carrier envelope phase shift frequency, phase offset frequency, which comes from the difference in speed between the pulse envelope and the carrier wave. The second frequency is also called the zero frequency signal because it starts at 0 on the RF spectrum. If we look both these features, the pulse becomes really stable, and we can clearly define the frequency of each compute as n times the repetition rate frequency, and pulse the carrier envelope offset frequency. But there is also a challenge. Well, the repetition frequency of pulse is easy to measure. We can measure the time of the pulse. But the carrier envelope offset frequency cannot be measured directly. So this made it hard to actually build an optical frequency curve at first. The professor UC Killer from the UC Killer professor come up with a solution called the X2F interferometer. This idea is very simple. Since we know the frequency of every compute, so we just need to find a component that twice the frequency and compute it with another compute it figure out the carrier of that frequency. Now it can image as this. You can see we get the twice frequency, which can be measured as 2n plus 2n times repetition frequency plus 2 times carrier envelope offset frequency, and we can find the orange computes, which is 2, which is this one. Sorry. This is an error. And the twice frequency is 2n times repetition frequency plus 0 frequency, and we can find the fundamental frequency is, which is n times repetition frequency plus 0 frequency. By times this fundamental frequency, we can get the frequency is 2n times repetition frequency plus 2 times 0 frequency. We using it to minus the twice frequency, we can get the carrier envelope offset frequency, which we call 0 frequency. So this is very simple. So the core question is how to get the second harmonic generation. We need to expand the optical spectrum of laser is to get the twice frequency. So the researchers used a special fiber which called photonic crystal fiber, which spells out the spectrum of the pulse. With this broad spectrum, it is easy to generate the second harmonic and use speed detection to find the carrier envelope offset frequency. And this is the step to get this one. First, we need to octave spanning supercontinuous generation, and then with selection, the filtering of applied wavelength space frequency doubling polarization adjustment, and then we temporal work of composition with noise detection, we can get the 0 frequency. Once we have it locked in place, give us a working optical frequency count. At this point, you should have a great understanding of optical frequency count. So let's go into the next. Next, we will show you how to building an optical frequency count from scratch. In this part, we need to look at what components are needed to build an optical frequency count system. The first part we introduce is an optical frequency count system, which we call an RF reference fully locked optical frequency count. As the name suggests, both of its key features are located to an RF reference, which is there. And usually this is a microwave clock. The structure is shown in this feature above, and you can see they have a femtosecond laser, which is also the usual short pulse laser, and we get F2F interferometer, and we get a several control system, and we get the PDE, which to get the repetition frequency. We also have a repetition rate locking system. And there is two reference source. So if we got these components, we can develop the locking system so we can make these two things locked. In this system, the system's stability is come from the microwave clock, which is it. The second type is which we call optical frequency reference fully locked optical frequency count. There are two ways to do this. One, lock both two features to the two ultra stable lasers, which makes the count more stable and reduce its line width. But this requires expensive hardware that most labs don't have. So the more common method is to lock the cavity length the to lock the cavity long strap to a single neutral stabilizer, which it can reduce the noise and also can narrow the bandwidth and improve the stability. And we lock another freedom we call the zero frequency, and also it called the carrier envelope offset frequency locked to a microwave reference source. The microwave reference source and the neutral stabilizer also have the same time base. And you can see this is the picture, and the most of the components in this is same as the RF reference fully locked optical frequency count, but with a slightly difference in it using a PD to get the bit node frequency, not the repetition frequency to lock. So for this system, it will get much more higher stability than RF reference frequency system. So what we can offer to build such optical frequency system, we can offer the microwave reference source, which is can generation from the 100 can generation the 0 to 400 megahertz or 100 megahertz to the 6 gigahertz. Second, we can offer femtosecond laser and the femtosecond bulk source with large modulation bandwidth. We can offer femtosecond lasers have two types. The first is the optical frequency concept source. It is look like this, and they have a several interface with PCT, EOM, pump, and we can also offer a monitor interface to get the repetition frequency. And the two output port. The one output port is optimized for the FCO detector. The FCO is also called the carrier envelope offset frequency. We also supply another femtosecond laser which can generation from 200 megahertz to 2 gigahertz repetition rate femtosecond lasers. And also we have offered the dual channel pump source, which have a high server bandwidth for the FCO locking. And in addition, we have two types of F2F interferometers, which we call the FCO detection. The first one is the fiber optical solution with using the aluminum fiber to generate the octaves, octave so-called continuous spectrum. And the second is on-chip solution. It's fairly self-developed. It need much low power. For example, if you're using the fiber optic solution, you will need the cost energy above 2 nano junior. But if you're using such on-chip solution, you can only need 0.3 to 0.5 nano junior. So it will low down the power. And both such FCO detection can generate much more higher FCO SNR. And after this, we also can offer the PD for detection. We can offer the 1.6 GHz PD. We can offer the balanced photo detector, which have low noise, and for more information about this balanced detector to get the bit frequency, please see our other videos with these components. Above, you will have almost everything you need to build an optical frequency consist. You just need to design your own server control system to finish this. But maybe you are thinking, I want to use an optical frequency count, but I don't want to build it myself because I'm not sure how to design a server control system, which is this part. Don't worry about this. We also offer a ready-made optical frequency count in a 3-unit classics, as shown in the image above, and this still have several microwave output and several optical output port and optical input port. And from these pieces, this is a reference for the time base 10 megahertz frequency and the FCO, the FR, the F bit frequency to get the external reference. This three is a monitor of the FCO and the monitor of the rotation frequency, monitor of the bit frequency. And this four is the output port which can give you individual for output pulse. The average power is above 10 milliwatt, and this one is to put the ultra stable laser in it to lock the optical frequency count to the ultra stable laser. And this is a panel we can just very quickly to lock the rotation frequency. You can see this will get the which called the auto lock. You can only one key to lock all the frequency. And we also offer a PC control software. You can see this. This one is this has 4 auto lock button, which auto lock Q frequency, auto lock FCO frequency, auto lock rotation frequency, auto lock bit frequency, and this is a measurement of the frequency. You can measure the rotation frequency, measure the FCO frequency, can measure the bit frequency, and this is a monitor of the several voltage. And this is a several control system. This is some detail of the several control system. You can see this is offset gain and the PID setting, and this is the message, and this is the periodic message. Of this, you can see in other video we have showed much more detail of such 3-unit instrument. And below this, we will show very quickly the performance of this optical frequency count. You can see we show the 100 megahertz rotation rate, and the tuning range is above 10 kilohertz. And this is the output spectrum of the for output. The center wavelength is 50, 100, and 60 nanometers. And the SNR of the single complex of the fundamental signal is about 75 dB. And the FCO spectrum, and we show the FCO spectrum and the bit frequency spectrum. The SNR is all approximately 35 dB. And this we show the stability of the rotation rate locking. carrier envelope offset locking, bit frequency locking, and this is this locking stability is good. Okay, and this is and we thank for your comment. And if you have much more question about how to build an optical frequency gun, how to get the 3-unit instrument, please connect us, and we will show you more and more detail. And please keeping contact us. We will show you more interesting mini class about our production and for some technologies. Thank you very much.